This is Chapter 9 of Solutions. Section 2 is Electrolytes and Nonelectrolytes. So an electrolyte is a solute that actually separates into ions when it dissolves into a water solution, an aqueous solution. And these ions then make the water electrically conductive. Okay? A lot of people know that water conducts electricity, but in fact, pure water without anything dissolved in it won't conduct electricity. You need to dissolve electrolytes in it to provide ions that can move and conduct the charge. Okay? In the body, electrolytes play a pretty important role in maintaining proper functioning of your cells and transporting ions and things like that. Okay? So electrolytes are very important. The first type of solute that we're going to look at is a strong electrolyte. Okay? And again, an electrolyte is something that produces ions when it's dissolved in solution, but a strong electrolyte in particular is one that completely dissociates 100% into ions. So for instance, with table salt, sodium chloride, when you dissolve solid sodium chloride into water, you don't get sodium chloride molecules. You get individual sodium ions and chloride ions. And they're each separate. They're each surrounded by their own shell or cage of water molecules that are separating them from one another. Okay? And so none of the compound remains in the joined state, in the sodium chloride state. They're all individual ions. That's what makes this a strong electrolyte. And since you generate so many ions when you dissolve a strong electrolyte into water, it actually makes the water conduct electricity very well. So you can run a current through this water with a strong electrolyte in it, and the current will carry well enough to light a light bulb. Okay? Now, just keep in mind, they're not providing energy from the water. There's just a battery off screen here, right, that they're not showing you in the picture, that these wires are connected to. So this is what's providing the power for the light bulb. But the current from the battery is being transmitted through the water. And if the water were not conducting electricity, it would be like opening the circuit, and so the light bulb wouldn't light up. The other type of electrolyte is a weak electrolyte. So anything that's not a strong electrolyte that fully dissolves is a weak electrolyte. Okay? These dissociate only a little bit. So they'll produce a few positive and negative ions, but usually a very small percentage. So hydrogen fluoride is a typical example. When you put hydrogen fluoride into water, you do get mostly hydrogen fluoride molecules, H bonded to F, and they stay that way. But a small percentage of them will dissociate so that you get some hydrogen ions and some fluoride ions, right? So here's a hydrogen and here's a fluoride. But this is a two-way process, right? So just like HF molecule can break apart into individual ions, there's also some tendency for those ions to join back together into an HF molecule. So you see that you have a two-way arrow here. Instead of just the regular one-way reaction arrow that we've been seeing, now we see a two-way arrow, which indicates that this is some sort of equilibrium with the reaction going in both directions. Okay? So we'll see much more about this in later chapters, but for now, all you need to recognize is that this double pointing arrow, this double-headed arrow, is an indication that this is a weak electrolyte, because it means both the ions and the individual molecules are present in solution. And since this molecule only produces a small percentage of ions, it will conduct electricity, but only weakly. Okay? So you still have the battery off screen, and the current comes through this solution. It doesn't really conduct enough electricity to brightly light the bulb, but it does conduct some, so the bulb still lights up a little bit. Then other than electrolytes, we can have some substances which are non-electrolytes. Okay? And these can dissolve in solution into water, but they don't produce ions. So for example, we saw in the previous video that methanol can dissolve in water because of all its hydrogen bonding potential. Okay? So, but when methanol dissolves in water, it just forms methanol molecules. Okay? So they go from the liquid state to the aqueous dissolved state. But other than that phase change, there's no other change in the molecule. Okay? It doesn't break apart. It doesn't form ions. It just becomes surrounded by water molecules, and so it's a hydrated solute particle. Okay? So the only difference here is the liquid turns into aqueous, or if you have a solid non-electrolyte, it will be solid turning into aqueous. Okay? And so since we're not generating any ions whatsoever in a solution like this, this solution will not conduct electricity. Okay, so you can put as much power through this as you want. It's not going to conduct electricity through the electrodes dipped into this water here, and so the light bulb is not going to light up. Here is a table that just summarizes some of those properties of strong electrolytes, weak electrolytes, and non-electrolytes, along with some examples in this final column over here. So you can review this when you're studying. But let's take a look at how we actually write the equations for electrolytes. So these are two examples where it's telling us they are strong electrolytes. Okay, and we want to know what the equation looks like for when these strong electrolytes dissolve into water. Well, remember the strong electrolyte means that you get only ions. Okay, there's no two-way arrow. It's not like you're just keeping it solid or changing solid to aqueous or anything like that. You're creating individual ions, or you're having the compound dissociate into individual ions. So what ions is calcium chloride made of? Well, the positive ion is calcium, Ca2+, and the negative ion is chloride, Cl-, and then there's two of them. Okay, so if calcium chloride breaks apart into ions, we're going to end up with one calcium and two chlorides. So which answer balances the equation in that way? C. Okay. A is incorrect because it shows no dissociation whatsoever, right? It doesn't even change the state, it stays solid, so that means no reaction, so that's not correct. And B is incorrect because this is not a real thing, okay? The Cl2- is not a stable molecule that we know of, okay? Cl2 is chlorine gas, but it's neutral, okay? If you tried to add an additional negative charge, an additional electron to a molecule of chlorine gas, it would not stick, it would not form a stable configuration, so that doesn't happen. Okay, what does happen is that an individual chloride or chlorine atom will gain one electron to complete its octet and become chloride, okay? And then you can have two of those to balance out the 2+ in calcium. So again, this goes all the way back to charge balance from ionic compounds. Similarly, with this second question, you have K3PO4. Okay, K is potassium, PO4 is phosphate, so this is potassium ions, K+, and phosphate ions, PO4 3-. Okay, and you have 3 potassium ions. That's what the subscript 3 means. Okay, and that this is balanced out. So we just look for the way to complete the equation with this information. So we have 3 potassiums and 1 phosphate. A. 3 potassiums, 1 phosphate. Okay. Again, B is not correct because it just shows solid turning into aqueous. That would be a non-electrolyte, so it can't be B. And C has some weird ions, right? It has a K3 with a positive charge. That's not a real ion as far as we know. This could be a real ion. Phosphide is a real ion. It's not super stable, but sure. And this is not a real ion. Okay, so other than this, they're not really showing any real ions. And you should also recognize that typically the polyatomic ions don't break apart or split apart into individual elements. They'll stay intact as an ion. Okay, so A is the correct answer here. So which of these following reaction equations represents the dissociation of a strong electrolyte? Well, let's go through them one by one. The first is showing NH3 combining with water to produce ammonium hydroxide. So this is not forming ions, so this cannot be any kind of electrolyte. B is just showing methanol going from the liquid phase to the aqueous phase. No ions are produced, so B can't be an electrolyte. C is showing sodium sulfate, and it's forming ions, so maybe that is. Let's take a look at D before we answer that. D is, again, just showing a compound going from the liquid state to the aqueous phase, so that's not an electrolyte. So C, which is showing ions forming, is our best bet. And then just to double check and make sure that it's a strong electrolyte, we can see that it has a one-way arrow. It's not equilibrium arrows. It's not showing you the double-headed arrows, okay? The one-way arrow indicates it's a strong electrolyte, so this would be C. Now let's take a look at a few more challenging examples. This question wants us to write the equation for the formation of a solution for each of the following. So they're going to describe a compound and how it forms a solution, and we have to first identify what kind of solute it is, and then write the appropriate chemical equation to express that. So the first one is the dissociation of K2CrO4, that's potassium chromate, a strong electrolyte, in water. Okay, so it tells us it's a strong electrolyte, so that's good. We don't have to worry too much about that. But then we just have to think about what ions it forms. So the most difficult part of this is maybe that you haven't dealt with this chromate ion too much yet. So this is, for instance, not on the list of polyatomic ions that you need to remember because it's just not that common. But you should still be comfortable enough with ionic compounds to recognize that if you have two potassiums here, that means you have K plus and K plus, and then this is an ion that's balancing that, then the CrO4 ion must have a 2- charge. Okay? Because each potassium has a +1 and there's two of them, that's a total of +2, so the chromate by itself has to balance that out. So what we're going to see once we actually put this into solution is we're going to get the formula on the left, the intact formula, K2CrO4, and it's going to be solid. And then this is going to dissolve, and we're going to do a one-way arrow because it's a strong electrolyte. Okay, you can write water over it if you want to. It's not really necessary. It's often left out. But it has to be a one-way arrow. And then you're going to list or write all of the individual ions. So first we have two potassium ions. And so we write two potassium ions, and they're going to be dissolved, aqueous. And next we have a chromate ion, CrO4, with a 2-, and this is aqueous. Okay? When you write an individual ion, you have to remember to write the charge with it. So when you're writing an ionic compound, the full formula for the entire compound, you don't put the charges. But when you're writing an individual ion, you do have the charge. Okay? So this is the formula, or this is rather the chemical equation for the dissociation of potassium chromate. B says the partial dissociation of the weak electrolyte H3PO4, that's phosphoric acid, in water. Okay? So this is a weak electrolyte, so we know we're going to start with the formula H3PO4, okay, which is going to start aqueous. Some of it will be dissolved just like that as that molecule, and some of it will break apart, and then it'll also join back together. So the weak means we need this two-way arrow. So when it splits apart, what happens is one hydrogen splits off of the rest of the compound. So you get one hydrogen, and then what's left behind is not phosphoric acid, but it is dihydrogen phosphate, H2PO4. Okay, so you've lost a positive charge from the hydrogen, and so now this ion has a negative charge. Okay, so this is a complex ion of two hydrogens attached to a phosphate. Okay, and this is also going to be aqueous. Okay. This is a weak electrolyte. The key here really is the double-headed arrows, okay, the two-way arrows. The last one is the dissolving of the solid sugar C12H22O11 solid in water. Okay, this is sucrose. This is table sugar. And when you look at this, it should be pretty clear that this is not going to form ions. So what happens is you have this covalent compound, C12H22O11, in the solid state. And when you dissolve it in water, it stays just like that. The molecules stay the same. They don't split apart. They don't break down. But the solid phase transforms into the aqueous phase because now each sugar molecule is surrounded by water. Okay? It's no longer being surrounded by a crystal network of other sugar molecules. So now it's in a different state. It's in the aqueous state. Since the most important property of electrolytes in solution is really their charge, it's useful to come up with a way to quantify the amount of charge in a solution. Okay, so instead of talking about how much mass we have in a solution or what number of particles we have in a solution, it's useful with electrolytes to sometimes talk about the amount of charge in a solution. So we can do this with the concept of an equivalent. Okay? An equivalent is the amount of an electrolyte or ion that provides 1 mole of electrical charge. Okay? So if you have a bunch of ions with a +1 charge, then in order to get a mole of charge, you would need a mole of those +1 ions. Okay? But if each of them had a +2 charge, then you would only need half as many to get a mole of electrical charge. Okay? So the equivalents correspond to the amount of electrical charge, not to the number of particles. In solution, the total charge of the positive ions is always balanced by the total charge of the negative ions so that they maintain charge neutrality. Okay? This does not mean that the number of positive ions is equal to the number of negative ions. They may have different numbers of particles, but different charges such that they still balance out. So for instance, if you have magnesium chloride, you have magnesium with a 2+ charge and chloride with a -1 charge. Okay? So you need twice as many chloride ions to balance out the magnesium charge. Okay? So this is, again, coming from charge neutrality. Often the concentrations of electrolytes in intravenous fluids are expressed in milliequivalents per liter. Okay, so the one equivalent is 1,000 milliequivalents. That's just what the milli prefix means. And then you can have a certain number of milliequivalents per liter. That'll be the concentration of the electrolytes in your blood. So here's an example of different types of ions with different charges and how many equivalents they represent. So like I said, if you have an ion with a +1 charge, so any of these, sodium, potassium, lithium, ammonium, these all have a +1 charge. So if you take a mole of sodium ions, that's going to be a mole of positive charge. It'll be 6.02 times 10 to the 23rd +1 charges. Okay? And so we call that an equivalent. Same thing if it's potassium or lithium or ammonium, they all have +1. So if you take a mole of them, then you get one equivalent. Okay? So this last column is the number of equivalents in one mole. Okay? If you take a mole of calcium ions, on the other hand, each calcium ion has a +2 charge. So you're going to have a mole of +2 charges, or you're going to have 2 equivalents. Same thing with magnesium +2. You'll have 2 equivalents. With iron 3+, you'll have 3 equivalents. Okay? So if you're looking at the ion, then the charge on the ion tells you how many equivalents are in one mole. And so you can use that as a conversion factor, we'll see in a little bit, to convert between the number of moles and the number of equivalents and the charge and all that. Also note that the sign doesn't really matter. If you're talking about positive or negative, is irrelevant. You can still talk about an equivalent of negative charge just like an equivalent of positive charge. So all of these -1 ions, chloride, acetate, dihydrogen phosphate, lactate, these all have a -1 charge. So if you took a mole of any of those ions, you would have one equivalent of charge. Okay? And so you can say one equivalent of positive charge and one equivalent of negative charge. Okay? But the equivalent unit itself doesn't specify either way. And then again, you have other ions here with multiple charges. So you have phosphate, citrate, those are both -3, and so they have 3 equivalents of negative charge per mole. Like I mentioned, in any solution, the total equivalence of positive charge has to be equal to the total equivalence of negative charge. Although the charge may be distributed among different numbers and types of ions, the total positive has to balance the total negative in order for the solution to be charge neutral. So for example, if you have a solution that's sodium and potassium and chloride, the sodium is 25 milliequivalents per liter, the potassium is 4 milliequivalents per liter. That means that the total positive charge from those ions is 29 milliequivalents per liter. Now, if the only other ion in there to balance that positive charge is the chloride ion, then the chloride ion itself must have a concentration of 29 milliequivalents per liter. Okay? It has to be exactly the same to balance out the charge. So in this case, the positive charge is split between 2 different kinds of ions, but all of the negative charge came from the chloride ions. So we can use this to do examples to convert between milliequivalents and moles of ions and things like that. So here we see the laboratory tests for a patient indicate a blood calcium level of 8.8 milliequivalents per liter. And so the two questions are, A, how many moles of calcium ion are in 0.50 liters of blood? And B, if chloride ion is the only other ion present, what is its concentration in milliequivalents per liter? So first we'll start by analyzing the problem as usual. We know that we have a half liter of blood, right? A is asking how many moles of calcium ion are in a half liter of blood, 0.50 liters. And we also know that the laboratory tests indicate that this blood has a calcium level of 8.8 milliequivalents per liter. Okay? So we need both of those pieces of information in order to answer this problem. And what we're looking for is not the charge or anything like that, it's the number of moles of calcium. Okay? And so we're going to need a couple of things. We're going to need to know a relationship between equivalents and milliequivalents, between moles of calcium and equivalents of calcium, things like that. Okay. And now we can write the plan to calculate the number of moles. So we're starting from a half liter of blood, 0.5 liters of blood. And so we want to take that volume of solution and convert it to milliequivalents of calcium. So we use the electrolyte concentration, 8.8 milliequivalents per liter. Once we have milliequivalents of calcium, it's a simple metric factor to get to equivalence, right? You just take the number and you move the decimal place over 3 places, or you take the number and you divide by 1,000 to get equivalence. Either way is fine. Once you have equivalence, then you want to figure out moles using really the charge on the ion. So the charge on the ion tells you how many equivalents you have per mole. So you can use that to go from equivalents of calcium to moles of calcium. Then the next step is to think about these conversion factors and see which ones we need. Okay, so the 8.8 milliequivalents per liter tells us that we have these two possible conversion factors, 8.8 milliequivalents calcium per liter or the inverse. Okay. The next one is that this is milliequivalents, but when we look at the charge on an ion, that's going to tell us the number of equivalents in a mole. So we want to be able to convert between equivalents and milliequivalents, which again is very easy. It's just a factor of 1,000 difference. And then the last one is converting between the number of moles of calcium and the charge of calcium. So 1 mole of calcium ions equals 2 equivalents of calcium ions. Okay? And so you have these two conversion factors here. And then we can just set up the problem so that our units cancel out. So again, starting from volume, we can use the concentration to convert from liters to milliequivalents of calcium. And then we can use the metric factor to go from milliequivalents of calcium to equivalents of calcium. So this will cancel with this. And then we can use the charge on the calcium ion to figure out the relationship between moles and equivalents. Okay, so remember, 1 mole of calcium ions equals 2 equivalents of positive charge. So we put the 2 equivalents of charge in the bottom to cancel out the equivalents there, and we're left with this unit moles of calcium on top. And so the answer we get is 0.0022 moles of calcium. To answer B, you have to recognize that the total equivalence of positive and negative charge must be balanced. So if we know that the calcium level is 8.8 milliequivalents per liter, then the chloride ion has to have the same concentration. It also has to be 8.8 milliequivalents per liter. Okay? Now that doesn't tell us how many particles it has in relationship to the number of calcium particles. We're not worried about that. We're just talking about the charge balancing. And the charge will balance when the two charges have the same milliequivalents per liter. So let's look at this idea that the charge can give you the number of equivalents again. Right? So in 1 mole of iron, you have Avogadro's number of particles, and each has a +3 charge. So that's really 3 Avogadro's number worth of positive charges. So that is 3 equivalents. In 2.5 moles of sulfate, SO4 2-, there are how many? So in 1 mole of sulfate, we would know that there are 2 equivalents. But we don't have 1 mole, we have 2.5 moles, so we have to multiply the 2 equivalents by 2.5, and we get 5 equivalents. Okay? So in 2.5 moles of sulfate ions, there are 5 equivalents. An IV bottle contains sodium chloride. If the sodium is 34 milliequivalents per liter, then the chloride ion is, well, again, has to be the same. Has to balance the charge, so 34 milliequivalents per liter.